Welcome all. Today we are going to learn about d block elements. What are d block elements? These are the elements in which last electron enters d subcell. These are present in the middle part of the periodic table, that is between s and p block elements. These d block elements are also known as transition metals. D block elements include group 3 to 12 of the periodic table. All our D block elements are metals. The last electron fills in n-1 d orbital. The outermost electronic configuration of D block element is n-1 d 1 to 10 and s 1 to 2, where n is equals to principal quantum number, that is equals to 4 to 7 for D block elements. There are three series of D block elements as under, that is 3D series, which ranges from scandium to zinc, 4D series from Y to cadmium, 5D series lanthanum, hafnium to mercury, that is having atomic number 80. Now we will be learning about physico-chemical properties, that is how they are physically and chemically different from each other. First of all, melting points and boiling points. So what are melting and boiling points? The substance at which the temperature at which the substance starts melting is known as melting point, whereas the temperature at which the substance starts boiling, which are in the liquid state, is known as boiling point. On the left hand side of our screen, you can see a graph of 3D, 4D and 5D series elements with melting point versus atomic number. You can see here that is the melting point and boiling point show no definite trends in the three transition series. The metals having the highest melting and boiling points are towards the middle of each transition series. You can see here chromium is having the highest melting or boiling point for the first one. Second is molybdenum, and in the third series is tungsten. W stands for tungsten, which is having the highest melting or boiling point in the given series. Whereas you can see almost gold, silver, and copper, they are just nearby to each other. Atomic and ionic radii. Now, what is the difference between the atomic and ionic radii? Atomic radii means that is the covalent radii, which is formed by sharing of electron pairs in a covalent molecule. The radii will be covalent, whereas if a molecule is formed by transfer of electrons, that means the ion exchange, then the radii will be ionic. Atomic and ionic radii value decreases generally on moving from left to right in a period. You can see we have again a graph versus the radius and the elements. You can see 3D, 4D and 5D series elements. Right, with the first is scandium to zinc. We have then yttrium to cadmium, then lanthanum, then hafnium to mercury. So we have scandium that is green in color. You can see the radius. Initially, the atomic radius is high, that is scandium, right? We can check it over here and then it goes on decreasing. The atomic radii for the elements from chromium to copper are very close to one another. Right, you can see over here chromium to copper. It is almost very close. The atomic radii of 5D series elements are virtually the same as those of corresponding members of 4D series. You can see that one is overlapping with another one due to the lanthanoid contraction. Why? This is because the lanthanoid contraction. Now, what is lanthanoid contraction? We will look into later in this chapter. Ionization potentials. So, what is ionization potentials? That means the energy required to undergo ionization. Ionization means removing one electron from the valence shell. Now, the energy required to remove that particular electron from its valence shell is known as ionization potential. So, what can we say about the first ionization potential? That is I1, ionization potential 1 values for the first four 3D block elements differ only slightly from one another. The value of I1 for zinc is considerably higher. Why? Because zinc atomic number is 30 and it is having completely filled d orbital, which is extra stable, completely filled in zinc atom. And as it is extra stable, more energy is required to remove an electron from the valence shell. Second ionization potentials for chromium and copper are higher than those of their neighbors because they are half filled. Now, as we have learned, that is half filled and completely filled orbitals are more stable than any other orbitals. So the value of I2 for chromium and copper are higher than those of their neighbors. This is due to the fact that the electronic configuration of Cr plus and Cu plus ions have extra stable 3d5 and 3d10 levels. There is a sudden fall in the values of ionization potentials in going from 2b, that is zinc group elements, to 3a subgroup elements. Oxidation states. The higher oxidation state of 4D and 5D series elements are generally more stable than those of the elements of 3D series. In short, it may be said that in going down a subgroup, the stability of the higher oxidation states increases, while that of lower oxidation states decreases. Transition elements cannot form ionic compounds in higher oxidation states because the loss of more than 3 electrons is prevented by the higher attractive force exerted on the electrons by the nucleus. Color. Transition elements with partially filled d orbitals formed colored compounds. Because partially filled d orbitals are ready to lose their electrons, and hence it is also d block elements are also known as transition elements as they can move from one state to the another state, that is they can undergo excitation, and while getting back from the higher oxidation state to the lower state, in between they transist color. And this is the way how G block elements impart color. Complex formations. D block elements are well known for forming the complex as well. Transition with element shows tendency to form complex compounds due to the small size and high effective nuclear charge, availability of low-lying vacancy orbitals which can accept lone pair of electrons donated by a ligand. Catalytic properties. Transition metals and their compounds are known to act as good catalysts due to variable oxidation state. They form unstable intermediate compounds and provide a new path with lower activation energy for the reaction. In some cases, the finely divided metals or their compounds provide a large surface area for absorption, and the absorbed reactants react faster due to the closure concept, as we have already learned in the adsorption. Adsorption means the process that is taking place on the surface. Magnetic properties. Magnetic moment, which is related to the number of unpaired electrons that we are going to calculate by using the formula mu is equals to under root of n into n plus 2. The unit Bm is known as Bohr magneton, Bohr Bohr magneton, as this formula was discovered by scientist Niels Bohr. Hence, it is known. Its unit is given by Bohr's magneton, where n is equals to number of unpaired electrons. Now, more the magnetic moment, that is, more is the value of mu. It shows the paramagnetic behavior. So, by calculating the value of mu, we can even determine whether it is paramagnetic or diamagnetic. Formation of alloys. D block elements are very good in forming alloys. Now, what are alloys? Alloys means the homogeneous mixture of a metal with a non-metal or a metal. To increase the physical property of that particular metal is known as alloys. So, as the transition elements have similar atomic sizes, hence in the crystal lattice, one metal can be readily replaced by another metal, giving solid solution and smooth alloys. The alloys so formed are hard and have often high melting point. Basically, we have an alloy of copper, zinc, interstitial compounds. What are interstitial compounds? Transition metals forms number of interstitial compounds in which they take up atoms of small size, example hydrogen, carbon, nitrogen, in the vacant space in the lattices. What is lattice? A particular arrangement, a definite arrangement of a molecule. The presence of these atoms result in decrease in malleability and ductility of the metals, but increases their tensile strength. Now, what is malleability? Malleability means when a metal can be converted into thin sheets by hammering is known as malleability, whereas ductility means the metals can be stretched into wires So that property of metal is known as ductility. Hence, the presence of these atoms means interstitial atoms results in decrease in malleability and ductility of the metals but increases their tensile strength. Next, we are going to look into about the inner transition elements. As I told you, that D block elements are also called transition elements. So now let's look into the inner transition elements, that is lanthanides and actinides. As we have looked into, that is 5D series, lanthanum, and then we have started with hafnium. So lanthanum and then other elements joined with it, which is known as lanthanides. So what are lanthanides? The F block elements are known as inner transition elements because they involve the filling for inner subshell, that is 4F or 5F. Now lanthanides consist of elements that follows lanthanum and involve the filling of 4 subshell, that is the 4F. I repeat, lanthanides consist of elements that follows lanthanum and involve the filling of 4 subshell, that is 4F. Electronic configurations you can see over here, that is xenon core 4F n plus 1 5D0 6S2, or else what we can write it, xenon core 4FN 5D1 6S2. And basically the lanthanides comprises of oxidation state is +2, +3 and +4. Coloration is many of the lanthanide ions are colored in the solid state as well as in solutions. The color is due to the FF transition since they have partly filled F orbitals. Even the colored can be due to the DD transitions, but for lanthanide, the color is due to the color exhibited by an element is due to the FF transition since they have partly filled F orbitals. Now, as I told you that lanthanide contraction is very important, so this we will be learning. So what is a lanthanide contraction? The steady decrease in the size of lanthanide ions with the increase in atomic number is called lanthanide contraction. The steady decrease in the size of lanthanide ions with the increase in atomic number is called lanthanide contraction. Now, how it is caused or why it is caused? So, as we move down the group from left to right in a lanthanide series, the atomic number increases. This is the general case, right? As we move down the group from left to right in a lanthanide series, the atomic number increases, and for every proton in the nucleus, the extra electron goes to 4F orbital. The 4F orbital is to diffuse to shield the nucleus effectively. Thus, there is gradual increase in the effective nuclear charge experienced by the outer electrons. Consequently, the attraction of the nucleus for the electrons in the outermost shell increases. The increase of atomic number, the size decreases. Now, few consequences of the lanthanide contraction. That is, first is separation of lanthanides. Second is basic strength of hydroxide. And third, it is similarity of second and third transition series. So what are the consequences of lanthanide contraction? That is separation of lanthanides. Second is basic strength of hydroxide. And third is similarity of second and third transition series. So what happens due to separation of lanthanides? Due to similar sizes of lanthanides, it is difficult to separate them. But due to lanthanide contraction, their properties slightly vary, that is, such as ability to form complexes. The variation in the property is utilized to separate them. Variation in the properties is utilized to separate them. Next is the basic strength of hydroxide, that is due to lanthanide contraction, size of M3 plus ion decreases. Now what is this then? Any metal of D block. And there is increase in covalent character in MOH and hence basic character decreases. The atomic radii of second row transition elements are almost similar to those of the third row transition elements because the decrease in size on moving down the group from second to third transition elements is cancelled by the decrease in size due to the lanthanide contraction. Next comes the actinide series. It consists of elements. Now actinide series, how lanthanides and actinides are differ from. Lanthanide contains 4F series, whereas actinide contains 5F series. It consists of elements that follow actinium and involve the filling of 5F subshell. General electronic configuration is Renon core 5F 0 to 14, 6D is 0 to 1 and 7 is 2. The elements are all silvery white metals. The melting points of the actinides are moderately high. General electronic configuration is Renon core 5s 0 to 14, 6d 0 to 1, 7 is 2. The elements are all silvery white metals. The melting point of the actinides are moderately high. I repeat, the melting point of the actinides are moderately high. The ionic size of the actinides decreases gradually along the series. The actinides have the ability to exhibit several oxidation states. It shows +3 to +7 oxidation state. However, +4 oxidation state is preferred in actinides. That means +4 oxidation state is more stable in the actinides. Some actinoid elements can exist in +6 oxidation state. Example, uranium, neptunium and plutonium. These all are the radioactive elements. Many actinoids elements, as I told, are radioactive. The elements beyond uranium are man-made. The actinides have a much greater tendency to form complexes than the lanthanides. Lower ionization enthalpies than lanthanoids. Actinides have lower ionization enthalpies than lanthanoids, as actinides are radioactive elements, so they lose easily their electrons and undergo ionization. So kindly go through these elements. You can see here we have D block and F block elements. Here comes your D block elements, that is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. And then the 4D series we have red, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium. And then we have 5D series. That is here only we will be taking, that is the lanthanum. And then after lanthanum we have hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury. Okay, you can see here that is 57 to 71 is separated as the different series of elements. That is here we have, okay, the lanthanide and the actinide metals. These are the transition metals that we were talking about. Then we have polar metals, metalloids, non-metals. So you can have, these are the noble gases that you can see where the noble gases are useful. That is, neon is used in advertising signs, argon in incandescent bulbs, krypton for the flashlights, xenon for the high intensity lamps, whereas radon is for surgical implants. Fine, then astatine, it is 17th group elements, which is radioactive medicines. You can see we have different uses of even D block elements, that is scandium for bicycles, then titanium for aerospace, vanadium for springs, chromium for making stainless steel, because as we learned that D block elements combines together to form an alloy. So iron and chromium, then nickel, they mix together to form a stainless steel. Manganese, then we have iron for making steel structures, cobalt using magnets, nickel for coins, copper has the highest ductility, so it can be used in wires. Zinc again converted into the alloy known as brass, so it can be used in making number of instruments. So just go through this, you will able to find that why we are learning these elements and where it is used in our day-to-day life. Thank you. Have a nice day.